Good evening, everyone. Thank you so much for coming to this week's Oxford Energy Networks seminar. Karen has just admitted everyone online, so welcome to everyone joining us online as well. And welcome in particular to Richard from Kyoto Fusioneering. And I know, having seen a sort of peek behind the curtains of Richard's slide deck, that he's going to spend the time introducing himself and his background as well, which makes my job very easy. So thank you for that, Richard, much appreciated. And so I won't dwell on this, but I will just say that it's really great to sort of continue the momentum behind the sort of fusion community here in Oxford and beyond, and recognise that actually this is the third time that we've had industry partners from the fusion industry speak to us within the last 12 months. So Kyoto Fusioneering this evening, which we're delighted to have, but previously First Light Fusion and Commonwealth Fusion have all been with us over the course of the last year. And I think that's a real testament to the growing momentum in this industry, and we look forward to finding out more about your journey and your approach in Kyoto Fusioneering. So thank you very much, Richard.
Thank you. Can everyone hear me? All okay online as well? Just want to check. Everyone can. Yes, thank you for the introduction. And I'm going to speak to you today with my perspective on the fusion system, fusion energy system, and actually not going to get to talking about my company until the latter part of the conversation. So firstly, going to take you through kind of what fusion energy is. I assume most of the audience know, but I'll give you my perspective on sort of how to explain it. And then sort of leading into where things stand today, a few key things have happened over the last decade. And then I will sort of tell you what our role in the sector is and some of the stuff that we're up to. So yeah, as an outline, I'll talk about me for just a moment and then talk what is fusion, talk about what I call the innovation paradigm shift, which is what my PhD research focused on. Talk then about that emergence of that new industry, then talk about Kyoto Fusioneering before I finish up. So about me, background in mechanical engineering. So I did my mechanical engineering at Swansea University before going to do a master's in nuclear engineering at Imperial College. I was part of the CDT, where I went on to study at the Open University under Bill Nuttall, Professor Bill Nuttall, who's an energy policy expert. And I was just saying to Paul earlier, my PhD took me in a very interesting direction, where I actually looked at innovation models applied to the fusion sector. So I sort of noticed something was happening in the sector, and that, you know, this sort of thing that was formerly just public sector R&D had shifted somewhat with the emergence of private companies and some funding coming from different sources. I was sponsored by Tokamak Energy, working on a part of my PhD on commercialization pathways. So I looked into a methodology called technology road mapping to look at the system of problems that they had, try and work out what is their path to commercial fusion. And along the way, spotted there are some major issues that no one had really sort of paid attention to yet. So resource supply, looking at things like tritium supply and so on as well. On the other side, so what I've done since then, I co-founded the company 5 years ago this month in Japan. That's a whole other story. If you're around afterwards, you can ask me how. It's fun. It's a good life lesson there. I'm now the field editor of the Journal of Fusion Energy and Commercial Fusion Sector and Commercialization. I'm an elected member of the IEEE Fusion Technology Standing Committee, which is the US IEEE professional organisation, and I'm appointed member as well for the Blanket Fusion Technology Committee at the IAEA. I'm also visiting senior researcher at Bristol and a board member of the Fusion Industry Task Force in the UK. So I'm quite busy at the moment, and I've taken on too much and said yes too many times. That's definitely something to learn. Don't always say yes. It's difficult. So I spent most of my time doing fusion stuff, but actually I wanted to do a little bit of something fun. So I was going to introduce you to stuff I do outside of work as well, just so you realise I am human. So I am certainly a man of the pandemic. I finished my PhD about 2 weeks before the pandemic hit. So I spent most of 2020 doing company launch stuff whilst remote, playing Call of Duty Warzone. Probably drinking a bit too much beer, definitely being nerdy because I absolutely love Star Wars. But I also love my wife and kids, which I always like to show there. And recently I cycled the length of the country back in June. So I cycled from Land's End to John O'Groats in 9 days, which was fun. And I got very fit. And sad to say, things have been a bit crazy work-wise since then, so I haven't really cycled much since, which isn't great. Hopefully that will change. Anyway, I thought that'd be a bit of fun to start with. Oh, and this is me at the Arsenal game the other day, so big Arsenal fan here as well. Luckily, they're not playing this evening. Okay, so what is fusion? We're going to go into back into the basics and start again here. Beforehand, shameless plug. If you want to see a version of what I'm about to present to you for the next 10 minutes of this talk, please go watch my TEDx talk as well. It does a lot better job of what I'm about to do now. It's probably slightly more compelling and something you can definitely share with people who may want to know what fusion is from the ground up. I'm going to go through this quite quickly just to give you a version. So we all know who that is. And in 2016, just before he passed away, he espoused that nuclear fusion was the thing that he would like to see as the sort of practical power source for the future of humanity. So fusion has the tick of Professor Stephen Hawking, which is great. So fusion, everyone knows, is the process that powers the sun and the stars. We're also all made of stardust. It's why we're all here. All the elements in the known universe, apart from primordial elements, were produced by stellar nuclear synthesis. And fundamentally, we can explain this by E equals mc squared as well. So it's the mass difference or the mass defect times by the speed of light squared is the energy released in a nuclear reaction you see in a star. And fundamentally, that's how we can use nuclear reactions, whether fission or fusion, to produce energy. So why do we care about doing fusion? Well, this thing's quite special. We've only got one of them as far as we can tell at the moment, certainly one that we can get to, and we've got to protect it. Because at the moment, we want to reduce the use of fossil fuels to fuel climate change. We want to reduce energy poverty, so bring up the standard of living, because everyone knows that energy tracks, well, perhaps you don't know, there are some very nice bits of data out there that show that energy poverty the economy is massively dependent on energy. And if you've got abundant energy, then typically your country and your people are doing better. This is definitely a big one now. Sorry, it's a bit of a slightly meta diagram, but energy security, which has become increasingly more important in a globalized changing geopolitical climate around the globe. And we want to reduce that energy dependence on energy sources controlled by a few nations. So that backdrop, climate change, energy poverty, insecurity and energy dependence is why we care. But why fusion? Well, the opportunity is that we think energy consumption and economic growth can be boosted by having a plentiful source of energy, and that's fusion. Returning the carbon debt to the Earth, it's looking increasingly likely like we're going to carry on producing carbon dioxide and greenhouse gases from burning fossil fuels. There's a good chance we actually have to start putting that back into the Earth somehow, decarbonising the atmosphere. And you need a lot of energy to be able to do that. And also we want to unleash the potential of our physical environment. I always say this technology is not the thing that sees us 50 years into the future. We don't get to fusion and go, oh, great, okay, what next? We've got to find the next thing. This is it. If we manage to crack this and we get it right, this could be the thing that sees us through the next millennia. So this really is an energy revolution that we're talking about. Now, that's the promise of fusion here, because we're not there yet. If we get it right, could be dispatchable, could be clean, at least in point of use. Geographically independent, certainly to a degree. Sustainable. I think, again, these are all things that can be challenged. I frequently challenge myself. We can use it for more than electricity. That's really important. So people talk about decarbonisation and reducing dependence on fossil fuels. Very, very hard to do if you look outside of the electricity problem. Decarbonising things like concrete production, steel production is really, really challenging to do unless you've got a huge amount of energy and process heat. Fusion can provide those things. It's inherently safe. Fusion's really, really hard to do, as we'll go into in just a second, and that also means it's really, really easy to turn off, because as soon as you switch off your power source, it's a passive reaction. And it's energy dense, super energy dense. So basically, you can produce 4 million times more energy than burning coal, oil, or gas, and about 4 times as much nuclear fission per kilogram of fuel. And hopefully, one day we can make it economical, but that's very hard to say for now. Okay, so how does it work? And maybe I can have hands up. Who is a physicist or a natural scientist in this room? Okay, so about half of you are going to have a good grip on what I'm about to say, but I'm going to go through it in lay terms and hopefully get everyone to follow along. Okay, so what we do is we understand at school there are 3 states of matter, right? Solid, liquid, gas. Well, okay, there's a 4th one. If you heat up a gas, superheated gas, you can turn it into a plasma. This is where the ions and the electrons of atoms dissociate, and this is something that's actually, these are probably LEDs, aren't they, realistically? But anyway, these are plasma lights in the ceiling. Let's just assume that is a plasma. There are plasmas everywhere in the world, and we know quite a lot about them, but fusion plasmas are a bit different. So when you have a fusion plasma, you have to heat up the fuels that you want to get to overcome a Coulombic barrier and actually collide together. So when you produce a plasma, you get this sea of ions and electrons, and this is actually charged. So you can act a magnetic field on it, and you can control what this plasma does. Now in fusion, what you've got to do is create a plasma, and you've got to have that plasma last for long enough, you've got to get it hot enough, and you've got to get it dense enough so that reaction will happen. And those 3 levers, hot enough, long enough, dense enough, you can pull any two or three of those levers to try and get the reaction going. Now what you need to do, and what we've been trying to do on the Earth for the last 50, 60 years in fusion, is try to get it above a certain level which is about 3 times 10 to the 21. Of these three together, the product of these three things, a so-called triple product, get above a certain amount so that you have more energy coming out of the fusion reactions that you create by making it hot enough, lasting long enough, and getting it compressed enough to make fusion happen. And you need to go a lot above that to then get way more energy out than you're putting into it. Did I explain that well? The TED Talk really is better than what I just said. Please go watch it. But fundamentally, that's what we're trying to do. We are trying to get fuels, hydrogen fuels, to collide and make fusion happen. There are two fundamental ways of doing this that we've followed over the last 50, 60, 70 years, actually. The left-hand side shows something called a tokamak, which is a magnetically confined fusion device. And this uses an array of magnets, as you'll come to much later in my talk. You can heat this plasma. So you're controlling your plasma with this magnetic field. You hold that in place and you can heat it up to temperatures you need, and you hopefully stimulate these reactions to happen. This is actually really low density. So you hold it for a really long time. You make it really hot. You've actually got very, very low density plasma. So you have to ramp up field on your magnets to hold it really stable for a long time, because these things like to wriggle around, and you've got to heat it up really high to get that reaction going. Okay. On the right-hand side, we have something called laser-based fusion. Now, laser fusion is actually really dense because you are focusing lasers on a very, very small point and pushing the fuel inwards, the fusion fuel inwards, and it's actually lasting for a very short amount of time. So you're pulling two different levers. You've got, on this side, you've got short time, high temperature, high density. This side, you've got high temperature, high confinement time, so how long you can hold it for, actually pretty low density. Everyone with me so far? Now, over the last 70 years, we've made a lot of progress, and the black line there is that line I spoke about earlier. If you can get things going above that, then you can do it. And there's a little hint, because there is a dot above that line, it shows we've done it, but I'll come to that in a second. Fundamentally, you can see this sort of trend upwards. We're getting closer and closer. Experiments are getting closer and closer to where we need to be. You know, we've got more energy out than we put into the reaction, but we're not quite there yet. Now, getting past that point has been regarded by someone that I know at MIT, Professor Dennis White. Some of you may be familiar with the name. He calls this the Wright brothers moment. This is the moment the wheels are off the ground, that we know flight is possible. This moment of getting more energy out than in is that wheels off the ground moment. Still a long way to go until we've got a commercial airliner, right? The Wright brothers didn't fly their first machine and go, great, now we're going to build a Boeing 777. They had to go a long way to get there, but it showed that it was possible to do it. So it's a really important moment. And this is a device from 1954, I believe. This is something called the Zeta machine, which is actually was based at Harwell, I believe, just down the road. And this was one of the first machines that sort of produced some really good results. Then they moved on to tokamaks, which is a Russian name. I'm not going to pronounce it because it's really, really challenging, but it's four different Russian words combined together. And this sort of got adopted as one of the best configurations for doing plasma confinement from a magnetic confinement approach because it was getting good early results. And we ended up with JET, which some of you may have seen. If you haven't, please go visit JET at Culham down the road, which is an amazing thing to see, although it is now actively being started to be decommissioned, whereas it ran for a very successful campaign for a long time. And finally, we got to this idea that actually let's keep building tokamaks, and we came up with this, which is a schematic of something called the ITER project. So ITER is a tokamak based in the south of France. This is a tokamak that involves China, Russia, the US, Japan, South Korea, the entire European Union, sort of the UK a bit at the moment, but not really, but kind of, yeah, we put a lot of money into it, but we came out of the agreement, so we're working out ways to get back in. And basically, it's an international project, a little bit like the space station or CERN. It's a science mission, but this was formerly the way to get to fusion. That's important, because I'll come back to that later. So this was stipulated to be the pathway to fusion. We've got to go via this machine, then we're going to get to the next phases. Okay, so this was essentially going to do that Wright brothers moment, magnetic fusion. But currently it's not constructed, and it's currently due to go first plasma in about a decade from now. And it was originally due to be first plasma in 2008. So it is a project that is about 30 years delayed. Bit of a problem when you're trying to move fast. Enter something else exciting. Laser side of the house. I said earlier, they're trying to get to really high density, high temperature plasmas. And in 2012, they ran the first shots on something called the NIF. It's in the US in California, National Ignition Facility. Now, this facility was supposed to provide that Wright brothers moment in 2012, and it missed it, and it missed it again, and it kept having problems, and there were delays, and so on and so forth. Hold that thought for just a second. So where are we at in terms of making that progress? Remember that graph I showed earlier with the progress? This is kind of the wishy-washy plot of that we've made real progress towards this point of fusion power break even, that Wright brothers moment. And then since then, we started building the ITER project. When NIF got delayed, things went a bit slow, a bit stagnant. We stopped making that progress towards that moment of fusion power break even, and we started to stall. That is until 2022. When the US Department of Energy, Department of Defense by the NNSA announced that they had achieved this break even on the NIF. So a decade late, but they'd done it, and it matched the models. And they did it again and again and again. And I've spoken to Tammy Ma, the director, and she says they've done it again and again and again, actually. So they've done it 7 times now, all with planned experiments, getting the results they expected. And I think the latest results actually see them get something like 2.7 times more energy out than they put into it. And you're thinking, great, so we've done fusion, that's it. Well, not quite, because that's not really how you commercialize technology. That's like I said earlier, you get a plane, you take it off, it takes off the ground, you go, yeah, we've done it, we've got commercial flight. There's a long way to go. So for NIF, just for reference, the amount of energy actually put into the particle, so the capsule, the fuel capsule, sorry, that might have produced more, 2.7 times more energy than was put into it. But the amount of energy to power the lasers and the cryo plant and all the systems and the guy with the coffee machine who was taking a coffee while he did the control panel, all of those things, I think it was something like 200 times more energy than they put into to the capsule. So the incident energy put in versus the incident out was good, but we had a long way to go to actually get the whole plant there. Does that make sense? Okay, so I think we've got the context of that's what fusion is, roughly how it works, and kind of the trajectory to now from a scientific perspective. And as I said, please don't go look at the TED Talk, because I think it'll be clearer just to consolidate what I've said there. Because God knows I've practiced that many, many times in front of the mirror, and I didn't practice this in front of the mirror. It was 2 years ago. So anyway, I want to take a step back and look at innovation. And you'll see why this is important in a second, because I think it explains a lot of where we go next and a little bit about where we've come from. So firstly, I'm going to define innovation. I'm not teaching you to suck eggs here, but when I got into this and started understanding innovation, and now technically a de facto expert in innovation, when people say, oh yeah, that's innovative, I'm like, okay, all right, let's dig into that, because I'm not sure that's true. People like to use innovation. It's probably the biggest known buzzword, certainly in the tech sector. When you get into the startup world, people just use innovation like it's going out of fashion. Now, innovation is simply the exploitation, useful application of invention. Now, what annoys me is that innovation is often used to describe an advanced or promising invention. But for an invention to actually constitute innovation, you have to actually have an application for it and make it useful. So it must provide some kind of use. Now, technological innovation is a thing. So if you prove, hey, look, I levitated this cup with my mind, great. Is that actually useful if I can only do it with this cup on this table? So a really weird example here. But fundamentally, technological innovation, because I've learned to do something with that cup. But unless I actually make that useful for society and I can start levitating, I shouldn't have gone down this road. I don't know where I'm going to go with this. Unless I start levitating other things that are useful for me to levitate, it's not actually innovation. It's just a remarkable technological innovation for us to achieve. So they are not innovations in and of themselves. Now, that translation of invention into something, and I'm going to say here very importantly, this is that can tangibly improve the quality of human life and or generate economic impact. Now, with fusion, we're trying to do both. There are other people in this world who just try to innovate. So if you look at any smartphone company, their innovation made them a lot of money. Could argue it improved the quality of life as well for a lot of people, for sure. But also there's often a downside to these things. Could well be the case for fusion. But anyway, I'm laboring the point. So what does technology to market look like? So we're charting the path of technology. So a market, it looks linear, right? We go from science to technology, application to market. So you typically have to overcome several peaks, whereby you say, oh, there's a lot of effort we've got to put in, a lot of money we've got to put in to prove that our technology can basically stay within the laws of science and that it works. And then we say, well, we've got our technology, actually we think it's got a really useful application. You run an experiment, do that again, another uptick in resource needed there. And then finally, you sort of show that actually you can make that commercially viable. You have to put a lot of work in to try and make it economic, right? That's the typical process of diffusing technology to market. Now, it looks like a linear process, but in reality, if you look historically at all innovation throughout history, it's dynamic. And what do we mean by that? Okay, so this should be viewed as a dynamic system, not as a linear process, because actually there are feedback loops that link from all stages. So this is a very instructive diagram. I expect you to look at it in detail now and try and think about where you might have real world examples in your industries or your world where that makes sense. But fundamentally, you have to think about the feedback from, is there a market for this? What does society want? Can this make money with the, actually, is this technically possible? Do I have the technology? Do I have the material? And you have to link these things up in a chain and make it work. Now, this seems very obvious, but a lot of people haven't thought about this when you're actually deploying stuff in the real world. And in a successful fusion innovation ecosystem, successful innovation ecosystem, you need to have a thought, you need to be able to understand what the requirements are of each of these parts of the innovation ecosystem, who the actors are, public, private, supply chain organizations, regulators, etc., etc. And also there's processes at the front end, that's the R&D side, and the back end, which is the application and the market side, and think about how those drivers impact other parts. Now, as I said a moment ago, historically, you look at advanced technology missions that had a high degree of technical risk, but potentially high, often societal reward. These were developed on a linear model, more or less. Now, these missions were done so, and these are almost exceptions to the rule because they required significant investment, and the goal was often not commercially oriented. So money and time had to go with things like the development of nuclear fission, which really was a bit geopolitical at the time. Certainly the Apollo, certainly the Apollo missions, and also the internet, interestingly, came out of DARPA in the US, and then see there were routes to Oxford in the UK as well. But yeah, fundamentally what happens is you go from science to technology and you have what's called a technology push approach. You say, I've got this thing, it can do this, and we need to do it. So we've got this thing, we can land it on the moon, and then we've done it, has now spawned an interesting commercial space race. But that took a very long time to materialize. They still did the thing. Their mission, their application was landing on the moon. In that case, that was the innovation in that case. It had to be, in that case, the Soviet Union getting to the moon. So how does this apply to fusion? So what I contend is that, you know, whilst fusion has been the subject of major R&D for the last 70 years, it's 1952, I think we really began looking into fusion, but that was actually a little earlier if you look at some of the fundamental physics that went on before. National labs ran the show. Private fusion companies didn't really exist. I'll come on to that again a little later. But naturally, those labs are going to be geared towards the front end of the innovation, right? They're going to be thinking about research development to prove the science, okay, and to understand the technology in more detail. They were not thinking about commercialization, and that's fine. That's okay. But with those focuses being on that fundamental research and some of those mission-led experiments, including the likes of the ITER program, you see on the right here, another schematic. That was the primary mission. And it was, okay, well, after we've done that, after we've done ITER, after we've proven NIF, we'll then start thinking about the next stages. We'll start thinking about those applications. We're not going to design this for those applications. This is a science machine. It's going to prove the science. We're going to understand some of the technology. We're going to progress it along. And then later, someone will come along and innovate, and we'll do it that way. So it's very much on the linear model. Now, what I contend has happened over the last decade or so, and I think we're still in it, but we're at the tail end, is that we've undergone a paradigm shift. So over the past decade, we've seen this science-driven model challenged by the emergence of 40 privately funded fusion companies. These have raised collective billions of dollars in investment. I'll show a graph shortly. And they promise to basically rapidly commercialize fusion technology. Now, rapidly in this sector still means probably decadal, but interesting. It's more interesting, in my view, what they've done to the state of the sector. That emergence has ushered in what I think is a new era, that paradigm shift, which, by the way, Thomas Kuhn described or defined as being the worldview underlying the theories and methodology of a particular scientific subject. So in this case, the development of fusion energy. Fusion science, no, there hasn't been a paradigm shift there. The science is still the science. You can't change the way we're doing plasma experiments, for example. But at the system level here, for fusion energy, we have. I really like this quote. I think it explains what I'm trying to get at here. Gordon Moore, who was one of the co-founders of Intel, he said, it's not science becomes technology, becomes products. That's the linear approach. It's technology that then gets science to come along behind it. So you test technologies and you go, hey, it'd be really cool if that could do that. And then you learn something about the science. So I talked about that feedback mechanism earlier. That's kind of what happens in the real world when you actually test stuff and put the rubber on the road. Sorry, that was a bit of a sideways one there, that slide, but it's interesting. hopefully checks are awake as well. It's always good when there's no text. So this is the investment into the private fusion sector over the last 10 years or so. You can see that a significant amount of capital, yes, that's $1 billion on the left-hand side there, has gone into fusion in the last few years in particular. So we're now, I think, at somewhere close to $8 billion invested in total over the last 10 years or so. Most of that's been in the US. Some of it has been in China, as you can see there as well. And there are companies all over the globe. So most of them, again, in the US, but maybe that's unsurprising. But we have two here in Britain, so Tokamak Energy down the road in Abingdon, and First Light Fusion up in Yarnton, north of Oxford. Several popped up in Germany in recent years. There's a couple in Japan, where my company is, and a few dotted around elsewhere, including one, for example, in Sweden and Australia most as well. That's been around for a long time, actually. So you can see the spread there. That's a useful map for you. And actually, just last week, I'm glad this came out, 900 million into a company in California. So this is still happening. This is still very much an active sector, and funding is coming into the sector right now. So what's different about these private fusions? Well, they're pursuing technical concepts that mostly originated from those labs or universities. So most of the companies out there, I'm not going to throw shade on the ones that aren't in this category, are trying to do something that someone had a program for. Or a professor in the 1980s, 1990s had a program that just couldn't get funding, but they thought it was an interesting idea and had some early results. Some of them are very, very close to the main line. Some of them are doing very close to the ITER type approach with conventional tokamak, using an advanced technology like, for example, HTS magnets. Tokamak Energy down the road are doing very much the same thing that STEP is doing, for example, in the UK. They're doing a spherical tokamak, which is a certain type of tokamak configuration, and they're using HTS magnets as their enabling technology to get to higher fields, and therefore better fusion. Now, as I said earlier, they're basically trying to turn those technologies into products as fast as possible. They're trying to get to fusion energy faster by building and testing things. And I contend that, as I said, that paradigm shift has happened. And actually, this has reshaped the landscape. So this is not me sitting here and saying to you, private fusion all the way, public fusion's out, it's not important anymore. In fact, quite the opposite. So what public sector did was they said, we're going to go from here to here. All private sector are doing is saying, well, we're here, but we know enough about these bits, so we're going to try and go really fast through those, as lower cost as possible, taking a good amount of risk, and we're going to try and get to this point. Forget this, though. We're not going to forget all the stuff here. For the most part, fusion developers want to actually work with the public sector to get that done. As I've written at the top there, these private sector developers, they're not just considering what may be scientifically possible or technically feasible, but they also think about what might work commercially. So going back to those innovation models earlier, they are looking at the market. They are looking at the application of their technology, what their investors are saying, we would like you to be able to do this. And then that's actually driving them. But those technical challenges that underpin all the concepts, it's still the same. They've got to develop materials. They've got to have a good regulatory framework. They've got to have supply chains. Nothing really changes. It's just the model, the approach to the problem that has changed. So what does this mean? Well, actually, we're moving into a world of public-private partnership, where the public and private sector are being told, if you work together, you can solve the gamut of technical challenges and also solve some of the challenges around how to commercialize this technology. And, you know, as I said, private sector cannot do everything alone. They're operating on this agile model, which is build, test, learn, go again. After you fail or succeed. But I think public-private partnerships in the US in particular, but certainly elsewhere. In China, these two bleed into each other anyway, but the public program and the private companies are starting to work together under official frameworks as well. So something called the milestone-based program in the US, and it's modeled on a space sector style approach where NASA and SpaceX work together on the NASA COTS program to try and get innovation happening faster. Different governments have got different approaches, but the UK, the US, and Japan have all announced new strategies for fusion over the last couple of years. China's also got one too, and you'll be unsurprised to hear. And governments have adapted. They've started to realise the private sector can't be ignored, and the public sector should be leveraged for the benefit of fusion energy as a whole, the benefit of their nations. And these countries are all working quite closely together. This has stimulated a lot of international collaboration. There's an official partnership between the UK and the US collaboration agreement between the countries. One is coming on Japan, I keep getting told, but it's been about a year since I was told that now, so still waiting to see what happens. I think the number of elections on both sides have caused slowdown. And there's actually a summit in Italy next week with the G7 specifically on fusion. So we'll see what comes out of that. Unfortunately, with that collaboration also comes competition. So the US and China are starting to draw swords on the fact that one of them wants to get there first. They're not sure which one it's going to be. So is there a new space race going on with fusion? Or is it more like the race to get the vaccine? Now, I wanted to look at this through two lenses. So firstly, through the geopolitical lens. Fusion's going to turn into a race internationally. Will we develop it more like the vaccine? So will it be actually, let's all get this together, let's all work on this, push in the same direction for the betterment of humanity? Or will we actually end up competing and trying to have primacy as an energy technology? Because this could be the thing that controls geopolitics around the world, just like oil does today. The other lens to look through this is on the mission itself. Both the Apollo program, often cited as that early stage mission for fusion, and the mission to get the vaccine are both quite similar. Because if we're aiming for the moonshot with fusion, it's a major mission still. And I'd argue that, in trying to get to fusion energy, we still require those early stage trials to test the experimental stuff whilst doing the building the runway stuff. If we do the linear approach and we just do the experiments, we don't think about regulation. We don't think about making this attractive to the market. We then have to do that later. During the pandemic, something interesting happened with the vaccine. Again, this is in my TED Talks. Please go look at the better version of me saying this, more curated version. They started working out how to get jabs in arms, how to mass manufacture things, how to get licensing done quickly, while they were still testing the efficacy of the drug in the first place. They weren't sure those vaccines were going to work, but they made sure that if they did, they were ready to go. And that's kind of what's happening in fusion now. So there's a couple of interesting lenses to look at. There's a geopolitical lens, and there's the mission itself and how we approach it. And again, I sense fusion is a bit of a geopolitical race right now, certainly becoming so, but also that this is not necessarily a bad thing for the innovation ecosystem as a whole. I'm going to pause for a second, just because I need to get a drink, but also any questions midway point. We're not midway, we're a bit past midway now, probably, but did anything I'd say not make any sense at all? Okay.
I think that so this parallel approach of establishing infrastructure at the same time as technology sounds really good, but doesn't that sort of burn funding and enthusiasm a bit faster than it would otherwise if you were just working on the technology?
Yes, absolutely it does. And as I'll come to a little later, for me, this is about the different actors in the system doing what they need to do. So there are certain organizations that specialize in market insights. You've got governments funding regulatory bodies and regulatory discussions. These are the really long range stuff, right? Companies like my own, which I'll get into in a second, we are focused very much on the supporting the here and now whilst building the next steps. We're not currently building steps 10 years away. We are building steps 2, 3, 4 years away. We're working out what the market's going to need to be successful in the next phase. So you're absolutely right. I think it's about being careful about who does what. We wouldn't get involved in, economic studies of fusion deployment at, grid scale, for example. But universities should be doing that sort of thing, because that's where they can play and do some really interesting studies and work out the direction to shift things. And those insights that come from those universities, they can be very helpful for the sector. But our company shouldn't be paying for that, for example, just like the lab shouldn't be paying for that. Just my opinion. It's about the actors. Okay, I'm going to press on, if that's okay. Okay. So hopefully what fusion is understood, and how things have changed in the sector over the last few years. It helps to explain what we do and where we fit in. So as I said, 5 years ago this month, we founded the company, which is 4 of us, and we're now up to about 140 people. So it's been a hell of a ride, and it's been fun. We've raised about $100 million, I think it's about $102 million in Japanese yen equivalent. It would have been more, but the yen's not doing very well at the moment. So it's unfortunate. We did a fundraise last year, then we did a bit of an extra fundraise and announced the same figure a year later because the yen had dropped so far in a year. But there we go. And we're now based in 4 countries, 5 technically if you include Canada, which we'll come to a bit later. And of course, here in the UK. This is a bit of a company overview there. Can you just see the details, including some of our investors, which by the way is a very Japanese thing to do, is to show the world who your investors are. Some people don't tell people, we tell everyone. So what's our vision as a company? It's what I said earlier. It's a society realized by fusion energy. We think fusion can do everything. We think it can not just do clean electricity production, but we could also do, for example, desalination of water for clean drinking water around the world, which again is another determining factor in well, humanity's prosperity. We think producing things like hydrogen for everything from ammonia production all the way through to hydrogen reduction in steel making could be important. We think looking at biomass gasification, where actually taking carbon out of the atmosphere, could be important. And there are various routes in which we think fusion can have a major impact on humanity. Our mission is to enable the fusion energy era. So this blue bit in the middle is NIF, it's ITER, it's whoever's developing a plasma. We aren't developing our own plasma. We're working on the bits on the outside. Probably the most instructive piece. Oh, and I should say, principally, these can be divided into 3 areas. Plasma heating systems. So this is the only area of our technology that's magnetic confinement specific. So if anyone's working on a magnetic device, this system's relevant. If you've got a laser-based approach, this thing isn't going to help. Explain why later. And then also on the thermal cycle, this is how we actually take energy and make it useful to turn it into hydrogen, use the energy for hydrogen or hydrogen production or something. And then the fuel cycle system is the piece that actually fuels the engine. Now I've got an analogy here for you, which is the first time I've tried it publicly, but I have used it privately a few times and it seems to have resonated. So I hope this is going to help you understand what we do. So think of a car engine, or rather the exploded bomb of a car engine. So that's bill of materials for engineers in the room, not bomb as in BOMB. So what you have is the internal combustion engine. And then you have things like the clutch, the gearbox that make up the drivetrain, and then you have the chassis, the exhaust system, the fuel tank, and yada, 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 and all the bits in between. Right? Let's think about fusion as a car, and this is one of my favorite cars, by the way. I'm not a big fan of cars, and it's a Japanese car, so there's a link there as well somewhere. So if that's the engine block, then this piece over here will be kind of like the spark plugs or the turbocharger or the air intake. Okay, this is the bit that provides the energy to the engine to get it going. Okay, you have to stretch the analogy a little bit because, of course, we don't have spark plugs in fusion. We have a plasma, and we don't have. We actually have no air inside fusion systems. They're normally vacuum chambers, very, very low pressures. Thermal system, that's your gearbox, your drivetrain, probably your chassis. Maybe a diff, right? Okay, this is the bit that actually transfers the power to the wheels, so you can actually operate your car, make it move, and make it do useful work, right? And the final piece, quite obviously, and sorry for the these are all the free stocking images I could find today of rusty old exhaust on this one, an exhaust and fuel tank, and basically this is how you fuel and inject the fuel and exhaust the fuel from your fusion reactor. So what you've got there: engine, fueling the engine, exhausting it, taking the engine, the useful work, and doing something useful with it, making sure you've actually got the ability to ignite the fuel in your engine in the first place. So that's what we do as a company. The only bit we don't do is the engine. And before I get on to what our business model is, again, this was something that I was forced to do when I started doing my research, because as an engineer, you think you know what a business model is, and then you go and read about it, like, yeah, this is more complex than I thought it was. So I'm going to do a couple of definitions of business models for you. The business model is a plan for the successful operations of a business, identifying sources of revenue, the intended customer base, products, and the details of financing. This is important. There's a lot to unpack, and I'm not going to do it now. There's a lot to unpack in this. You've got to make sure that what you're making is actually needed. You've got to make sure you can actually make what that thing is, and you've got to be able to actually fund it as well in the first place. So you've got to link these things up, as I said earlier. This is what private companies do. We are not here as a research organization. We are here to commercialize research. Now, why is it important? Well, getting the business model and technology strategy in the context of something like fusion is right, because to actually achieve something commercially viable, you've got to have a competitive advantage over your competitors and over the market. And that's what we think we have. Because what we do is we're running perpendicular to those in the sector. So this purple box here shows all these private fusion developers, all these public programs. That's ITER, that's the JET program at UKAEA. That's the UK's national program, Japan's national program, as well as all the private sector companies. We are developing things that all of them need now, today. We are generating revenue as a company. We're already generating revenue quite a lot as well. And that is important because to your question earlier, sir, you have to make sure that you're both delivering today and planning for the next steps. The planning for the next steps is what I'm going to talk about mostly next. But So in simple terms, if you're a plane company, we're making the engines. If you're Boeing or Airbus, you don't make your own engines. Rolls-Royce or GE make them for you because they're the best in class. And they collect their supply chains to supply all the turbine blades and materials and filters and so on to make that happen. So part one, this piece, the spark pluggy bit that I spoke about. Now, a gyrotron, it's a machine, a piece of kit that you can use to heat a plasma. So you can heat plasmas through something called electron cyclotron resonance heating. So what you do is you fire microwaves at a certain frequency at high power into a plasma, and you can transfer the power from that microwave beam into the plasma, into the electrons. You get the frequencies right, you can heat up those electrons enough such that they're so energetic that they can pass their energy onto the ions in the plasma. Those ions in the plasma are important because if you get them to the high enough temperature, you can actually get the temperature of the plasma to make fusion happen. So you can see how important technology this is. Now, there are other methods of plasma heating. This is not the only one, but we think this is the one that can be most efficient. And we're very lucky to have, our CTO is the world's leading plasma gyrotron specialist. So we're very happy to have him on the team. His name is Sakamoto, Keiichi Sakamoto. We are already selling these technologies. We've sold 2 to the UK National Programme and 1 to a private company in the UK. We have gyrotrons at various frequencies, about 1 megawatt output power, and a wall plug efficiency of about 50% at the moment. We can go all the way up to continuous wave operation on these. So we have these as products available now. If you actually are interested in buying a gyrotron, please come and order. But please bring your checkbook and we can talk. But fundamentally, we have sold 8 off of these so far. So this is the majority of our revenue because this is what the market needs today. So we've taken a technology that we knew would work, and we had the understanding of. To actually take that to market was more challenging. You have to jump through qualification loops, you have to do quality control, you've got to get your supply chain organized. But now we have a very robust setup to be able to sell these into the market. It also so helped that our main competitor was Russian, and no one's allowed to work with Russians anymore. We'll leave that one to the side. So we've delivered 2 gyrotrons to UKAA. That's them there. There's a nice video there if you want to go find. If you type in gyrotrons Kyoto Fusioneering UKAA on YouTube, you find a nice little PR video there. And we've also completed the FAT, which is the factory acceptance test. I think we've actually done the SAT, the site acceptance test for a gyrotron to a private customer as well. We're also working on the R&D side. We've done some high voltage power supply R&D in Japan, working with a Japanese company, Nichicom. And we're also now working on a higher frequency gyrotron, which will basically be able to go for some of those. So if you know some of these companies around the world that are looking at these high field devices using stronger magnets, if you go to strong magnetic field, you typically need to go to much higher frequency of gyrotron, so possibly upwards of 300 gigahertz. Now, at the moment, that's very challenging, but we're looking into ways to be able to increase that frequency to see if we can actually heat high field plasmas. So that's the first part. Second part, I'm going to group into one because they are very much overlapping. So this is the thermal and the tritium fuel cycle piece. And what we've got is something called the Unity program, which I hope you're going to love. So remembering this is this piece, and just for reference, it's that drivetrain, powertrain, power delivery, useful work, and the fueling piece. But first, we're going to take a step back, and I am actually going to teach you some fundamental fusion engineering here because I think it is important. So I talked earlier about a fusion reaction, and we're going to get a little bit more detail here. So I didn't mention the specific fuels, which in fusion are deuterium and tritium. Now, the reason they're in deuterium and tritium, you can ask me afterwards if you're interested, but fundamentally, these are the easiest fuels to do fusion with. So we make fusion happen, yay, by some form of magic, and then we produce helium and a neutron. Now, the helium remains within the plasma because it's a charged particle. We have to exhaust that out through something called a diverter in the magnetic fusion device. In a laser machine, you still have a cavity chamber that you still have to get it out. But anyway, this is the important bit for us as a company, because anyone dealing with the plasma has to get that out and actually use the energy from that in the plasma for their concept to work in a certain way. Okay, but this piece is uncharged. Neutron is an uncharged particle, so it will go anywhere. And this goes out of your plasma and into something called a breeding blanket. Now, does anyone know what a breeding blanket is? Okay, there's a few in the audience. Right, so what a breeding blanket does, when we talk about how fusion could be a self-sustaining fuel forever, the breeding blanket is the thing that does that. At the moment, you're burning fuel, and you go, well, where's it gone? How can this be sustainable? Well, this one is 1 part in 6,700 atoms in water. So if anyone's, okay, my water on the table, there's a lot of deuterium in that I could get. That isn't. We can produce it from lithium. And if that hits into a lithium atom, it splits and it becomes tritium and helium. That breeding blanket, you can extract that tritium from the lithium in the blanket and close your fuel cycle. So this one's really, really abundant, and this one can be produced from lithium, which in the context of this, by the way, is really abundant. For about 1 year for one power plant, it's about 50 kilograms of lithium burnt up that you need. So you need a lot larger amount in the reactor, but it's not anywhere near as much as you might think. Now this gets hot because this is imparting its energy. So you've also produced your fuel in the reactor, in the blanket, and you've also made it really hot. So you need to transfer that energy out to run a steam turbine to make electricity, for example. So this thing here is the kind of interlocator between the fuel cycle and the power cycle. Okay. Hope you followed that. If not, please ask me clarifications afterwards. Fundamentally, in graphical form, this is how it works. Okay. Well, who did that? That's wrong. That should be helium-4. Sorry, that's not me. This is my colleague. Okay. I'm showing my hand that I didn't make these slides, but I really like them. So other than that, they're really good. So deuterium and tritium, they come together. They produce a neutron and helium, which isn't shown. That neutron flies out. It flies into this layer, which is, well, M actually stands for multiplier there, but we won't get into that. M stands for materials or multiplier. It can split sometimes into 2 neutrons. That's what multipliers do in a blanket. This is all nuclear physics. Again, I can talk about that if you've got any questions. And then those hit into the lithium, produce tritium, and you remove the tritium. So graphically, hopefully that helps explain what I said earlier. Sorry if it was a bit more confusing. Now, this tritium piece is a critical path challenge for fusion. It affects every single major system, and it affects performance, safety, and cost. Every time you want to move fast in fusion, tritium will be the thing that applies the brake. You haven't got enough of it, you can't produce enough, it's too expensive to get in the first place, it gets trapped in materials, yada, yada, yada. We can go through those if you're interested. It's not something you bolt on either. You hear a lot of people in the fusion sector saying, oh yeah, well, we'll do the fuel cycle afterwards. No, this is integral to the operation. It's not an afterthought. It affects how your plasma operates. It affects which materials you can choose. It affects how you design your breeding blanket. So this is something that we at Kyoto Fusioneering value very deeply and say this is the piece that's one of the most complex engineering systems, not just in the fusion sector, but on the planet. It's a very, very complex piece of kit. It gets very hot. It's very spicy from a radioactivity point of view as well. And we're going to design it well. It's a complex system. So whilst we've got some facilities that provided some insights into materials development or how you actually do the fluid flow around a blanket system, how you extract your tritium from the blanket, we've still got a lot of work to go. I'm not going to go into this diagram, but I've included it because there's a link to our paper down there on this topic, and you can find some more information. We've actually got a follow-up paper to this coming out later this year as well. But basically just to signify that your blanket system that I just mentioned is here. I haven't even talked about the fuel cycle yet. You know, I mentioned that car exhaust system. Well, in fusion, because you don't want to lose your tritium, you don't just release it to the environment like you do with a car. You don't just get rid of your NOxes and your sulfur dioxides, and then just get rid of the rest of the environment. You actually have to keep your tritium in the system. So when you exhaust it from a fusion reactor, follow my hand, so hopefully this is helpful. Exhaust it from the fusion reactor. You've got helium. You've got unburnt fuel, deuterium, tritium. You've got particulate matter from inside the vessel. You've got to clean that up. You've then got to separate that. You've got to store it. You've got to get rid of the nasty stuff. You've then got to refuel that again, but sometimes you just want to store it for a while. Sometimes you've got long-term storage. I'm not going into details here, but the point is it's a complicated system. This is not just a fuel cycle like you think of in a car. Okay, that's the key takeaway. If you do want to know more about this, I gave a keynote on it last month at the conference, and I have got the slides and the presentation recorded as well. So if you want a copy, please let me know. I'll give it to you. Okay, so on to Unity. So what we're doing is trying to crack the fuel cycle. So this is both the tritium fuel cycle and thermal power cycle. And the interlinking piece there, if you like, is that blanket piece. Okay. So building 2 facilities called Unity 1 and Unity 2. So we had the original names. Unity was 1 program initially, and then we split it into 2 for reasons I'll explain in a second. And then I said, oh, we should do a Unity 2, and then that name stuck. So be very careful when you're naming things, because names just stick if you say it first time. So on the fusion thermal cycle, take a quicker look. So it's being built in Kyoto in Japan. This is something in a second you'll see. There are actual photos. This is real. This is basically to test initial pieces of blanket technology. We've got a liquid metal inventory containing lithium, which is the breeder we're going to be able to use in that blanket. And we're going to have things like a heat exchanger, a hydrogen extraction system, an impurity removal system, high temperature test sections, magnetic field test sections, so we can test what happens to the fluid flow when it's under magnetohydrodynamic stress from magnetic fields. So this is something that we think we can really make use of to actually test technologies and go, yeah, we've not only looked at this in isolation, we've looked at these technologies in an integrated setup. We've understood how they've worked, and even in some cases probably qualified in the first stages what that technology needs to do, so that if a customer comes along and says, we need to know how to do that, we can go, yeah, we've got experience with that. And if we don't have experience, we can run an experiment. Or maybe we decide that we actually want to do something slightly different in the future, running, for example, with a different working fluid. The 3D schematic of what it's going to look like, and yes, before you asked, the pipework is orange. We made an executive decision that it would be. It cost money, but we decided it was worth it. So this is what it actually looks like, and it's slightly more red than orange. I was kind of disappointed it wasn't like luminous orange, but anyway, this is the facility, and the commissioning of the base loop is now completed. So this pipework you see here, by the way, the pipes are really thin. This is a lot of insulation around the piping to keep it hot. This has got a liquid lithium lead, so as I said earlier, as the breeder flowing through it. And we've got things like a tritium extraction system, so testing how we can get tritium out, but this is a non-active facility. There's no tritium here. Luckily, you can use deuterium as a proxy. And as I said, we've got that magnetic field, the heat exchanger installed in there as well. And the idea is to actually demonstrate that you can get heat from that lithium lead loop through a heat exchanger into helium and actually run a steam turbine. In the first instance, not with helium, of course, that'd be with water, but also we want to run a Brayton engine off this thing. Sorry, I may have gone a little bit deep there, but for me to not go deep on this thing. It's a complex facility. And then on the fuel cycle side, what we want to do is test the other part of the system. And about 2 years ago, almost to the day, I was, of all places, in Romania at a conference, and I had sushi in Romania, which was very good, actually. That probably, sushi in Romania, not the normal thing you would do. And I was with a colleague from CNL, Canadian Nuclear Labs. This is the government's laboratory in Canada. And for whatever reason, again, I can dive into it if you're interested. Basically, Canada is the world's leader when it comes to tritium technology. So we had a conversation, and I said, we should be doing something together because you guys have got all the tritium, you've got all the knowledge, and you've got the site. Could we do Unity 2? And he said, yeah. So we set up a call. We talked about it. We got our business team involved and their business team involved, and we got all the legal stuff. And then we formed a JV, joint venture. So we actually have now an official joint venture with the Canadian government, and we're building Unity 2 in Canada. So the idea is we deliver Unity 2, operate it, and then we'll supply fuel cycle components to the industry. So we've joined forces between Japan and the Canadian government to be able to do that. Not the Japanese government, sorry, to be clear, our company in Japan and the Canadian government to make this happen. What we want to do is close key technology gaps in a bold timeline. So again, going back to that gyrotron piece, we are developing technologies that people need tomorrow, but we're working on them today. But then we're also doing the integrated pieces of work and the hard, really hard technology problems of tomorrow so that we're ahead of the game. So hopefully, again, this illustrates the answer to your question earlier, that we're working on the next steps whilst also making sure we've got things people need now. So things people need now, for example, certain pumps, membranes, diffusers, certain materials, and we have a supply chain orchestrated through the fact we're building facilities like this that we're able to then actually bring together to deliver stuff to the market today whilst innovating the next steps. Use that word very choice earlier. This is the building it's going to go into. Another reason to go there was, as I said, they have the site, they've got the license, and we're all set up to do it. If you walk down this corridor, all your tritium is there. So it's already on site, and that building is licensed, and we've just had the license, the regulator has said, yeah, you're allowed to do Unity 2 in there. It hasn't changed the license case fundamentally. You're still using tritium, you're still using some of the technologies. Fundamentally, what we want to do is take the technology readiness level from where this blue area is and move it up towards pink. So this is the ultimate mission of Unity 2, is to get to the point where we say, yep, we understand most of the tritium fuel cycle that's required for a fusion power plant, such that we could actually build this thing. And it's on schedule. I think we're actually about 4 weeks behind after a year of official project planning. So I think that's pretty good going for a project of this size. And yeah, as I said, we've got the Canadian nuclear regulator confirms the scopes within the existing license. I think also the conceptual design is now complete, so I should tick that one off as well. It's a global team working on this project. That's some of the team from Canada in Japan. That's our facility in Japan. This is us then working in Canada at some workshops. And if you are in the fusion sector, even if you aren't and you want to get into it, there's a conference called Tritium 2025, which is next year in Ottawa, and there'll be a site tour to Unity 2. It'll be about midway point through construction next September. So please go and have a look there. We are on the organising committee, I believe. So yeah, you can get some further info if you want it. Key supporting activities in this area. So on the blanket side, Unity 1 and Unity 2 are testing the core technologies, but what we are interested in from the blanket side is where the market is now. So what do we do with those technologies? How do we actually design those systems into customers' needs now? And that really comes through looking at things like neutronics, tritium transport, looking at reliability assessments, safety assessments, thermohydraulic and thermomechanical analysis. And my team in the UK, which I'll come to in just a second, are working on a lot of these areas now to actually be able to apply our technology and take it to market. Because you can't just say, here's my piece of kit. Great, you've got it. You have to actually work out a way to integrate that with people's machines. And we also want to steer the market in a certain way, making sure people say, yeah, that technology looks like a really good choice. You guys have done a really good job at working out how that's going to work. So we're going to go with you. And we also have a materials development program where Japan is the world's leader in something called silicon carbide composite technology, which is very high temperature, potential high temperature operating material, about 1,000 or more degrees Celsius. And this is one of the things that we're trying to develop to see if it's possible to use this material for fusion. We have a dedicated program on that. On to the very last slides now. Just wanted to give a sort of, because we're in the UK, I wanted to kind of give a sense of what we do in the UK. And I've got a team of about 14 people in the UK now. And we're currently hiring for a couple of positions in the engineering team. So that's kind of what the size we're at. We're about 120 in Japan, about 4 or 5 in Europe, and about 5 or 6 in the US. So the UK is our biggest subsidiary. The UK is a world leader in fusion. I really hate to say that because the last government really liked to say that we were world leading in everything. We'll yet to see what this new government does. But anyway, in this area, it really is true. Culham down the road is an exemplar of that. We've got a very strong national programme and government commitment to this area. UK AEA hosted the European Jet facility and also pioneered its own approach with mast upgrade, which is where our gyrotrons are now supporting, by the way. So mast U at Culham, our gyrotrons are waiting to heat plasma when that's up to speed. It's also been a sort of pioneer internationally on regulatory side, so looking at how to regulate fusion to be innovative, and also on the sort of research side, including Oxford University, by the way. There's a huge materials focus at Oxford University, as well as plasma physics. So again, you probably know about that, but they're key areas for this in this university particularly. I've highlighted the STEP program because this is sort of a really ambitious government program, which is going to cost probably in the order of tens of billions in my view. The work's already started. The UK government's poured hundreds of millions into this over the last 4 or 5 years. They've just reached their first concept design, which you can go and find details of, although I would like to see more information actually, but anyway, it's by the by. And they also announced alongside it something called the Fusion Futures Funding. Now, this was as a result of Brexit. We pulled out something called Euratom. This was the agreement with the Europeans, and that funding was reallocated towards fusion to say, I think we can do something useful with that money in the UK. So I'm really glad the former government decided to put that in, and had a big remit there to support industry as well, not just putting money into the labs, into the R&D, but also into thinking about those next steps to commercialise technology, albeit that a lot of that is still around nearing. And the UK has got, as I said earlier, those partnerships internationally, including with Japan, which we also foster. Now, what do we do in the UK? Our specific mission as a subset of the company's mission is, well, after launching in 2021, we sort of established ourselves in the UK to lead fusion innovation in the UK and support development of the UK market. So we're just trying to steer things in the UK towards what we think they need to be, and also provide engineering and technology development and deployment in the UK. We sell things into the UK like tritium systems, technologies, gyrotrons, but also engineering services. So most of my team in the UK provides engineering services to the UK market, but we're also developing our own capabilities. So I mentioned earlier on the blanket side that we're sort of developing some of those techniques in modelling, thermohydraulics, et cetera, to be able to sort of understand what our own technology needs to be able to do, pushing the bar higher. And our purpose is really to drive growth over here. So the new Labour government will like that because growth seems to be the word they